Hello everyone, welcome back to the video lectures on image and speech processing. So we have been talking about our image compression model techniques, how we have talked about different model techniques like Halfman, Shannon, Fanon coding, arithmetic coding. Then we talked about LZW coding, which is used for spatial redundancy. Then we talked about block transform. After that, where is this block transform used? We have talked about JPEG and JPEG 2000. So these are the compression models we have talked about. So in today's video lectures, we will be talking about a compression model technique which is called as the predictive coding. Okay, so this is a very important topic which is used in the real-time applications nowadays. Right. So what actually is predictive coding is? It is for redundancies of the closely spaced pixels. If they are closely spaced pixels, like the continuous pixels we are trying to reduce the redundancy of those group, then we use this predictive coding. Okay, and we are coding only the new information in the each pixel. Say suppose we have an image and we have a continuous background. Okay, say suppose we have a image of this sort and I have a scenery like say suppose mountains like this. So if we observe here, the sky here, whatever it is a continuous and it is constant. There is very slight difference maybe in color, or the intensity values will be very minute difference. So this can be called as the redundancy because it is like difference. If there is small difference, if we code it, we are using a lot of information. If we say that this all pixels are same and we are trying to code it using a single value, then we are able to reduce the redundancy. We can do only this when the information that is there, it is not, we are not losing it, right? So such kind of redundancy we can use this predictive coding. So we are going to code only the new information in each pixel. So not the exact information, but the new information if it exists from previous pixel to the next pixel. Right? So why are we going for this predictive coding is it achieves a good compression. I mean the compression ratio is good, so we are able to reduce the redundancy more, and we are able to achieve it without using a computational overhead. Okay, so without using a computational overhead, without like previous data like calculations overhead and or computational overhead, and good compression technique is obtained, and it can be either error free or lossy. It can be either lossy or lossless. It is based on the required application, right? So this kind of predictive coding is useful in that way. Now what are we doing is the new information of the pixel is, how are we getting this new information of the pixel? We are defining it as a difference between the actual and as well as the predicted value of the pixel. So we are basically in predictive coding, we are coding only if there is a new information in consecutive pixels. If there is no information, then we are not coding it. So that is how we are able to achieve our compression model. So we have to get the new information. Means what are we trying to, how are we getting this new information is, we are calculating the difference between the actual as well as the predicted value of the pixel. So what is this, how is this done? We will see using this block diagram. So we have two types of predictive coding. As I said before, it can be either lossy or lossless. So here we are starting up with lossless predictive coding. So in lossless predictive coding, we have a encoder as well as a decoder. We have two models, which is an encoder and decoder. So we have an encoder and decoder, and both in encoder and decoder, the predictor or whatever a block we are using it, that we are calling it as a predictor. So the block predictor is identical in both encoder as well as the decoder. So what kind of predictor we are using in encoder? The same replica we are using in our decoder. If we are not using this predictor which is identical, then we will face lot of errors. So we have to be careful, and so this is a very important point, that at both encoder and decoder the predictor is identical. Then what are we doing is, we are taking the successive samples that we are giving to an encoder. So the encoder, what does it do? It predicts the or estimates the each sample value based on my previous values. So if I have a pixel right now, if I take a pixel intensity value based on my previous intensity values, I'll compare this present pixel value with my previous pixels values and check out what is the new information. Based on that, I will predict a intensity value, so that we are rounding off to the nearest integer value. Okay, so based on my previous samples, I'm estimating the present pixel value. So that how are we doing based on my previous samples. So this predicted value, if it is like f cap of n and the actual value is f of n, then the difference between these two, that we are calling it as error, that error we are giving to a simple coder. Simple coder is basically like run length coding technique or half-man coding technique. So this error is being coded. Okay, not actually the intensity value, but we are coding using the error. Right? So let me just take a small example and explain how does this work. Say suppose the input sequence. What is the input sequence? We have the input intensity values. Let it be 10, 11, 12 and 15. Okay. Now, I have the first intensity value to be 10. So when the first 10 comes here, we don't have any previous pixel values, right? So this predictor cannot detect any value. So this becomes a 0. So this first symbol, the first E of n will be 10 only, because we don't have any predicted value. Now, next we are going for 11. Okay, so next sequence is 11. We have 11. So based on this 11, our predicted design, we are going to predict what is the value of this pixel. Okay, so based on that, the predictor can predict, say suppose 10. Previously we had 10, so it is predicting the value of this pixel will also be 10. Assume. Then we are rounding off to the nearest integer, because we are using discrete images or digital images. So the nearest value will be 10. So this now f cap of n will be 10. So what will be the error? The actual value is 11 and the predicted value is 10. So the next symbol code, or the next symbol that we are sending to the symbol coder is 1. Now let's come back. So when we come back, the next sequence is 12. Right? So based on my previous pixels, I had 10, 10, 11. So the predictor now probably it will predict the design. We can predict it to be 11. It will predict it to be 11. Right? So we are rounding off to the nearest integer 11. So now this f cap of n is 11. So now what will be the error now? It will be the actual value is 11. The predicted value is 11. So this error will be 1. Right? So it will go on. Now I have my sequence to be 15. Right? So based on my predicted, what will be my predicted value of my next pixel? It will be 12. Right? So the predictor is saying that the next integer value, which is just the summation, next value, right? So I'm summing next predicted value, I'm saying it to be 12, but actual value is 15. So what will be the error now? 15 minus 12, that is 3, right? So these sequence, which is the 10, first error is 10, next error is 1, 1, 1, 3. So this sequence is given to the symbol coder, and this sequence, which is like your symbol coder, can be half-man or run length coding. So this sequence is coded. So this is how we are able to get a suppression, because for representing 11, 10, 12, 15, we require more number of bits, but when we have 1, 2, 3, the error is smaller. So the symbols that we are coding is much smaller, so we require less number of bits. So this is how, using a predictor, we are able to achieve the compression. Right? So, and we are not actually coding, we are coding the actual intensity value, we are coding the difference. So sometimes the en might be 0. The error might be 0. If we have sequence of zeros, then what does that mean? We don't have any difference or new information in that pixels, in a row of the pixels. So using this run length coding technique, we can code it to be a single vector, and we can reduce the number of bits to be much lesser. So this is how the lossless predictive coding is done. right? So when we come to the decoder stage, what is happening? We have a encoder, so that is we are having the inverse operation, which is the symbol decoder, and we, with whatever predictor we are using in the encoder, the same predictor we are using here. So using the same predictor, we are able to get a decompressed sequence. Okay, so this decompressed sequence can be obtained in this way: estimated value plus error. Whereas in my encoder, how did I get my error? As actual value minus the predictor value, right? So the same inverse operation we are doing in our decoder, right? Say suppose I am in my previous example, whatever I've discussed, I've discussed only the previous sample. So when I was discussing about a level, I discussed about is just previous sample, which is 10. So if I'm talking about my next pixel value, which is 12, I was just talking about only my 11 pixels. So I considered only one previous pixels. Say suppose if I'm considering the order of the predictor is m. Order of the predictor is m. Then what does that mean is I am going to consider m samples, m previous samples to predict the present value. So that f cap, the present value f cap, whatever I'm predicting, I'm using m pixels value. So this is the order of m, a predictor m. So if the order is m, then I'm considering m samples, and my predictor value can be written as in mathematically in this form. So f of n minus 1. So I'm considering my present to be 0, f of n if I'm considering. So my previous m values I'm going to consider, which is f of n minus 1, n minus 2, so on till m minus 1. Right? So many pixels I'm going to consider. And this alpha, whatever we are saying, it is the predictor coefficients values. It can be 1, it can be any constant, it can be negative. It is all dependent upon the predicted design. Right? So the basic predictor, whatever we are designing, is the summation predictor. Right? So we are based on my previous pixels values, based on my coefficients, I am defining my next pixel value or my present pixel value. That whatever we have discussed, it is the lossless predictive coding. So what we are discussing now is lossy predictive coding. There are two types of predictive coding. One is lossless and other is lossy predictive coding. So lossless we have discussed. We are assuming that there is no error as such. So when we are going for lossy predictive coding, what actually is happening is we are introducing a quantizer block. Okay, we are introducing a quantizer block. So to maintain the at the decoder and as well as the encoder part, to maintain the similarity, we are placing the quantizer block in between my predictor as well as my nearest neighbor, nearest integer round off. Right? Let me just go back to my lossy. Okay, in my lossy, I have the encoder model to be predictor, nearest neighbor, and this is in the feedback loop. Right? This is kind of a feedback loop. So what am I doing here is, instead of placing the nearest integer here, I'm placing a block which is the quantizer, and that quantizer based on my predictor value, that is creating an error. So placing this quantizer is creating an error. So why do we actually require to present the quantizer is, we are actually making a trade-off between the reconstruction error and the compression performance, right? So how much reconstruction error is possible and what is the compression performance that we need to achieve, right? And even the number of sources, computational sources that are available, how many bits are available. So based on that, I have to reduce my error to be, or my sequence, input sequence which I am coding to be much lesser, right? I require much more bits lesser. So for that, I am introducing a quantizer. So what is happening here is, if I have an input sequence, right? So that same input sequence, it is given for my predictor also. So based on my previous predictor, I am achieving a some predictor value, right? Usually. So based on that predictor value, I am achieving a error which is E of n. So now that is my lossless predictive code. Now what is happening here is, I have an input sequence which is performing a quantizer, right? So based on that, I'm having an error e cap of n or e dot of n. So based on that, a new predictor is getting generated, right? So new predictor value is being generated, that is based on my quantizer error. Previously the predictor value was dependent upon my input sequence, my previous input sequence, whereas here my predictor value is depending upon my quantizer error, which is e dot of n, right? So if you assume, if you see here, that value plus my previous predicted value, based on those values a new predictor value is being given. So that predictor value will be given to here and it will generate this e. So this is a feedback loop that is being generated here, and this en whatever it is being generated, that is given for my symbol encoder value, right? So this is how we are able to achieve a compression in my lossy predictive coding. Since we are introducing a quantizer, since we are introducing this quantizer, we have a loss of information. There's a possibility of loss of information that that is actually maintained when the reconstruction error and the compression performance. So we require how much compression and how much reconstruction error is possible. So based on that, the trade-off is maintained so that we introduce this quantizer, right? So it is also here we're able to digitalize the intensity values also using different quantizing methods. So based on that, that is given for my simple coder that we just compressed, right? Here what does it do? The quantizer, as I said, it maps the prediction error into a limited range of outputs, right? So that is denoted by E dot of n, and this is establishes the amount of compression and distortion that is available in the lossy predictive coding. Now, what kind of quantizing model that we are using is the delta modulation, right? So we are using a delta modulation. It is a very simple quantization method, okay? It is a very simple quantization method. What is the delta modulation is the equation here it defines. So this E dot of n, which is the quantizing error, is equal to positive E or positive error when the error E of n is greater than 0. If the error is negative, then we are giving the value as minus E. So this is all, this value is dependent upon my application specific, right? So based on my application and the reconstruction error, that is to a trade-off, based on that we are giving this value. So what is this E of n, how is this achieved, and how is the prediction value is done is this new predictor value, which is f dot of n, is equal to E dot of n and the f cap of n, right? What is this f cap of n is equal to the alpha of f dot of n minus 1. Small mistake here. The summation of alpha of f dot of n minus 1. If my order of my order of my predictor is m, then I can write f cap of n is equal to summation of I is equal to 1 to m alpha of f dot of n minus I. So this is similar the equation whatever. So this predictor is based on my summation values only. So the previous summation values only, that predictor only we are using it. So what is the summation previously in lossy predictor coding? We had summed the previous input sequences. So that based on that we have predicted the present pixel intensity value. Here what are we doing is we are summing the previous predicted values or the after the quantizer predicted value whatever we have. So based on those predicted values we are predicting it to be new predicted value, right? So f dot of n is equal to E dot of n plus f cap. F cap is equal to alpha of f dot of n minus 1. So similarly we have the decoder. There is no change in my decoder, right? So whatever quantizer I have a small block which is dequantizer which will be performed. So based on that predictor and the symbol decoder, right? Let's see a small example here using which is like performing the lossy predictive coding, and we are assuming that alpha is equal to 1. So that means all the predictor coefficients are equal to 1. What is this eta is the quantizer definition. So whatever we have seen here. So if E of n is greater than 0, then we are giving it as positive E, and this E of n is less than 0, we are giving it to be minus E. So this minus E is given here to be a delta modulation quantizer, and that is given to be the error to be 6.5. And here I is a sequence of my input intensity values, which is given by 14, 15, 14, so on and so forth till 82. Right? So from here, it is actually a grey image that we are considering. Right? So how to solve this? We are solving it in the form of a tabular form. Right? So what is the input sequence? This is a sequence numbers, right? 0, 1, 2, 3, so on, and how many digits we have, how many intensity values we have. So what is this f of n? The intensity values, which is 14, 15, 14, 15, 13, so on and so forth till 82. Okay. Now, based on at my encoder stage, what is my predicted value? What is my predicted value? It is dependent upon my previous summation values, which is the sum, right? So at my first input intensity value, which is 14, I don't have my previous predicted values. So this is 0, right? So my f dot, the predicted value, the final predicted value is now 14. Okay. Now let's come to my next input sequence, which is the 15. So when I come to 15, what is my previous predicted value? It is 14, right? So here, whatever is the final predicted value that we have got, that is now is the predicted value, which is 14. So what is this error? E of n is equal to the f of n minus predicted value, which is 1, right? So now if this error E of n is greater than 0, then we give the value to be plus eta, right? So this eta is equal to 6.5, which is defined in my question, right? So I have defined it to be 6.5. So what is this f dot of n? That is equal to f dash of n is equal to f cap of n plus E of n, right? So this is my value. This is my equation, which we have seen previously. So I have got this f cap 14 plus 6.5, which is 20.5. So this is my predicted value of my lossy predictive value. Next comes to my sequence, which is 14, right? So now 14, when we are considering, what is the previously predicted value? It is the 20.5. Right? So this is 20.5. We are going to consider it to be the predicted value. Now, what is this E of n? If we consider what is E of n, this is equal to 14 minus 20.5, which is equal to minus 6.5. Or, right? Minus 6.5. The error is minus 6.5. So this error is less than 0. So what will be the E dot of n? So it will be again minus 6.5. If when it is minus 6.5, so what are we doing here? Again, this formula f dot of n is given by f cap of n plus E dot of n. So what is here? We get it to be f cap is equal to 20.5, right? So this is equal to 20.5 minus actually plus of minus 6.5, because the error is this. So we have got it to be 40. Right? So now the next sequence again is 15. So 15, what is the previous predictor value? It is 14. The error is 1. Since the error is 1, which is positive, we are giving the E dot of n is equal to 6.5, and the predicted value now it will be 20.5. So let's consider the small example. Next sequence we will try to do. So this is 30. So the previous predicted value is 20.5. Right? So the error is 13 minus 20.5, which is E of n, right? So this value is minus 7.5, right? So that is equal to minus 7.5. This error is less than 0. Error is less than 0. So we are giving it to be minus 6.5. Now what will be the predicted value? Predicted value will be, which is f dot of n is equal to f cap of n plus of E dot of n, right? So that is equal to 20.5 minus of 6.5. So that is equal to again 14. Right? So this actual input sequence is 13. We have predicted it to be 14. The previous 15 was given 20.5. So there is a lot of errors, right? No. Let's go back. Let's go back and we will check the how is decoder performed. So we have got this sequence. The sequence now for the decoder part is this coded f cap of predicted value, which is equal to 14, 6.5 minus 6.5, so on and so forth. So based on that, we are able to retrieve back my f dot of n, right? So I'm able to retrieve back my f dot of n. So this f dot of n and actual sequence we are trying to compare to calculate my error. So this is called as the prediction error, lossy prediction error, right? So we have understood how the coding is performed and decoding is performed. So this predictive coding is basically used when we want to we have lot of information in the continuous pixels to be constant, then we want to reduce the redundancy in those pixels, then we can use the predicted value, because we are going to access, or we are going to code only the new information that is there in the pixels, right? After we convert what is the new information, that is existing in each pixels, then we can give it to a simple symbol encoder, which is run length or half-man coding or Shannon coding, or the various coding techniques that we have used to decrease the number of bits further. So this is how compression model or image compression model of this sort is designed, right? So this further information or further examples can be seen here in digital image processing by Gonzalez, right? Thank you.
Like, share and subscribe. Hit the bell icon for more updates.